Okay, so what are we doing today? We're going to talk about the last method for computing volumes, and this method is called volume by shells. Okay, and then one other section, which is 6.5, and that's going to be length of curves. So let's go ahead and start with a motivating example. I'm not going to do all of the nitty-gritty math details, but I want you to understand a major difference between the volume by shells method and something like disk or washer method. Let's say we have the following scenario. We're going to take a rectangle. Okay, so this is our R, right? So we would say we have a bounded region. Here's a rectangle. We're going to rotate it about y-axis. Okay, now you can visualize this fairly easily. What you're going to generate is a cylinder. Okay, if we do this, we get this solid, that's a cylinder. Okay, we actually know how to compute the volume of a cylinder from geometry class. We know how to do that. Okay, but this is calculus, so we're computing things a little bit differently. So now let's go ahead and think about how will we apply the disk method in this scenario. You would say, okay, let's go ahead and take a bunch of planes and slice our cylinder with these planes that are perpendicular to the x-axis, right? And then look at the cross sections. Okay, so the cross sections will be these disks. Okay, we know how to compute the area of a disk. Okay, so if this is the case, you can visualize it like this. Okay, how do we actually find the volume of a cylinder? One way to think about it is that we're stacking infinitely many of these disks, right? So we compute these areas and then just add them up, infinitely many of them, right? Okay. I can only make finitely many pictures, but that's the idea. Okay. You find this area, that's the area of the cross section. What's the area of a circle? We know that one, right? This one is pi r squared. In our case, that r would be the function, right? This is the general formula. We would just plug in whatever our function is. Okay, so that's your main idea for the disk method. Now, if you have a washer method, that means what? We have a hole in the middle, okay? But the idea is exactly the same. Now, what about the shell method? Okay, let's just take a look at this cylinder. I want you guys to understand the major difference. With the shell method, we're going to go ahead and take the same cylinder, except now we're not going to be stacking disks on top of each other. Instead, think about now, you're gonna take the cylinder and wrap it in with paper, right? So one way to think about it, I'm gonna wrap it with paper, okay? And I'm gonna take a look at the area of the paper that's required to wrap my cylinder. And think about it, you're just peeling it off, right? So, and that's going to be one area. And then we're going to just keep looking in, right? So the area of one, that's one shell. And then here's another shell. And then there's another shell. And there's infinitely many of these shells that are fundamentally different than, you know, when you stack all of these disks on top of another. Okay, so and that's what we're doing with the shell method. Okay, we are not stacking areas, we're rather peeling them off and then keep going from the outside in, right? Okay, so that's one way to think about it. And I think somebody made a comment. Let me see, what's the comment? Volume by onion layers. Yeah, pretty much. Okay, these are the layers, and of course there's infinitely many of them. And now let's take a look at the area of this surface of, let's say, paper. If you were to wrap the cylinder in paper, how much area of the paper do you need, right? Okay, well, if I unwrap this paper, what's going to happen, I'm going to get another rectangle, right? Okay, we know the area of a rectangle. What is the area of rectangle? It's width times height, right? Okay, width times height. Okay, but now if you look at the cylinder that we have here, let me make a little bit more layers here with different colors. Okay, how do we compute these quantities, the width and the height? Okay, well, we know what this one right here is. So the area of circumference, that would be this side right here, which is the width. Okay, and the area of circumference, we know that formula. It is 2 pi r. This is from geometry, right? Okay, and then here we just have our height. And what is this height? Okay, this height would be determined by the function that is given to us. Okay, and also by the limits of integration. So now, if you go back to this formula right here, you see what this formula is actually telling us. This is 2 pi x. Okay, 2 pi x is your 2 pi r. Okay, and this one right here, this would be the height of your rectangle. Okay, or whatever, you don't necessarily get a rectangle, you can get something else, right? So that is the explanation of this formula right here. Of course, you do not need to know the whole derivation, but I would like for you to see the major difference, the fundamental difference of what we're doing with the two methods. Okay, so let me stop here for a second. This is not a rigorous derivation of the formula, but do these pictures make sense to you guys? And what I mean by, let's say, picture number 1, that's this cylinder where I'm stacking these circles on top of each other, versus picture number 2, where I'm looking at that same cylinder, except that now I'm kind of decomposing it in a different way. Does this make sense? I see some answers. Absolutely. Good. All right. So now we know the idea of this. Now let's go ahead and actually apply this. Okay. All right. So I have 4 examples for you guys, and you will see that we're going to have 2 examples where we rotate something about the y-axis, and then 2 more examples when we rotate something about the x-axis. And the setups fundamentally will be the same, but we will have different variables of integration, and that's going to be important. So let's take a look at the first problem. We have the function y is equal to 1 plus x squared quantity to negative first power. We have y is equal to 0, x is equal to 0. So these are our axes, and then x is equal to 2. We're rotating this about y-axis. Okay, I'm going to be highlighting important things about y-axis. With shell method, whenever we have rotation of r about y-axis, you can go ahead and make your note here. Everything is going to be in terms of x, which is not the same as the disk and washer method. Remember, when we were rotating r about y-axis, we had to write everything in terms of y, but that's not the case for the shell method. Okay, so this is going to be important. Let's go ahead and make a picture here. Okay, let's see. So what is the picture going to look like? We have 1 over 1 plus x squared. Okay, I don't expect you to graph this by hand. You can look at Desmos. You'll see you're going to get a curve like this. Then it's bounded by the x-axis, y-axis, and x is equal to 2. Okay, so here's my r. And we're going to revolve this r about the y-axis, right? This is y, this is x. Okay, so you can visualize this object. It's not a cylinder. So we don't really know how to compute the volume of this object just using simple geometry. Okay, there is no formula for that, not that we know of. So that means we need to apply a different method. Okay, so what is my function here? This is y is equal to 1 over 1 plus x squared. Okay, that's you can think about it as your top function because we're gonna need to find the height. Okay, how do we set up our formula? V is equal to the integral. Okay, everything is in terms of x. I'm going to emphasize this. The formula says 2 pi x. Okay, something goes here, dx. And then we have f of x minus g of x. So we need to decide what the height of our shells is. Okay, the height would be this piece right here. Okay, the one that I'm highlighting with orange. All right, so what is our top function here? 1 over 1 plus x squared. The bottom is 0 in this case. Okay, so now we need to decide what the limits of integration, okay, are. The limits are from 0 to 2, right? This is your limit here. Okay, everything is in terms of x. I'm checking everything. 2 pi x times f of x, that's my top function, minus 0, which is fine. Okay, that's my bottom function. That gives me the height of the shell. X goes from 0 to 2. The questions I see, and this stays in terms of x no matter which axis it is revolved around, the answer is no. Okay, once we're revolving around x-axis, we're gonna be having a setup in terms of y. Okay, so now we have it set up. Okay, we just need to integrate this. If I simplify this just a little bit, what do we get? This is from 0 to 2, 2 pi x over 1 plus x squared dx. Okay, that's my integral. How would you guys integrate this function? Let me pull up 2 pi. Anyone has an idea?
Would that be the inverse tangent?
Would it be? It kind of looks like, but not quite. It would have been okay if there wasn't that x in there, right? Inverse tangent is just 1 over 1 plus stuff squared. But that x makes it not suitable, right?
Can you u sub?
Yes. When in doubt, always try u sub. Okay, so what's our u sub? U substitution. Okay, so that would be 1 plus x squared, that's your u. Then we get 2x dx, that's your du, which means x dx, that's 1/2 du, right? Okay, you can find the antiderivative and then go back to your original limits if you wish. I prefer to take care of the limits right away. So with my u substitution, what are my limits? Okay, if x is equal to 0, then u is equal to 1. And then if x is equal to 2, that means u is equal to 1 plus 2 squared, that's 5, right? Okay, so now I can rewrite my integral as what? Let's see. It's 2 pi times the integral with new limits now. We go from 1 to 5. And what do we have here? We get 1/2 du over u, which is easy to integrate, right? 2 and 1/2 cancel out. We get pi times natural log, excuse me, of absolute value of u, We go from 1 to 5, and then we just evaluated. This is pi times natural log of 5 minus natural log of 1, which is 0, right? So what is your final answer? Pi times natural log of 5. Okay, so where would I put this? So let me see right here. Pi times natural log of 5. That is our final answer. Okay, of what? Cubic units. This is still a volume problem. Okay, let me stop here for a second. Any questions? Any of the steps unclear? What do you guys think? No comments? Okay, I'll take this silence as no comments. Okay, then we're moving on to the next problem.
I think it's 11 plus x.
Was there a question?
Oh, sorry. I think it was 4 plus x squared. I think I might have gone wrong with activity 1 for number 4.
Oh yeah, so we'll take a look at activity 1 next time. But about this problem, is this problem okay?
Yeah.
Okay. And let's go ahead and take a look at example 2. Okay. What is this example here? We have the following setup. Okay, so the first thing that you guys want to do when you work with problems like this, make a nice sketch. It doesn't have to be super precise, but it's good to have a good picture of what you're working with. So we have y is equal to 3x. It's a straight line that goes through the origin, slope 3. And y is equal to 3, so that's a horizontal line. X is equal to 0. So we are rotating this triangle also about y-axis. Okay. Now we know what we're going to get. We know that it's going to be a cone, and you could find the volume of this cone by just a geometric formula or by disk method. Okay. But that's not the point. We want to see if we can do a different method, right? So now I'm going to highlight important parts again about y-axis. That means everything needs to be in terms of x. Okay, limits, functions, and the integration itself, right? Okay, so this point right here where they intersect, this is 1, 3. What is my volume? One step at a time. 2 pi x. This is my width of the shell, right? Okay, and of course it's going to be different width dependent on what my x is. Okay, 2 pi x. What about the height? Okay, what is the height? It's f of x minus, oh, it's f minus g, right? So f minus g, whatever those two functions are. Okay, so the top function is y is equal to 3. This is your height right here. These are all your heights. So that goes in here. This is your 3 minus the bottom function is y is equal to 3x. 3x. Okay. So put it in a different color because a lot of times this is the step that's a little problematic. All right, what are the limits? Where are we going? Remember, this is in terms of x, so I'm looking at the range for x. We go from 0 to 1. These are my limits of integration. Okay, this is the hardest part, just setting things up correctly. Okay, once you set it up, typically you see that this function is not difficult to integrate. This one is polynomial. Nice and easy, so we're going to factor out what? So I'm going to pull out 2 pi. We go from 0 to 1. And if I distribute my x, I'm going to get 3x minus 3x squared dx. Okay, that's easy to integrate. So this is 2 pi times 3 over 2x squared minus x cubed. We go from 0 to 1. At 0, this expression is 0. At 1, it's easy to compute. 3 over 2 minus 1. So that's 1/2. 2 pi times 1/2 pi. Okay, that's our volume. Okay, and we can go ahead and check because the formula, the geometric formula for cone, for the volume of the cone is known. The volume of the cone, okay, is given by 1/3 pi r squared times h, where r is the radius of the base. Well, in this case, it's that top, right? Okay, and what do we get if we just plug in our numbers? We'd better get the same thing. So we get 1/3 times pi. Okay, what is the radius? The radius is 1. What about the height? The height, so let me show you what the radius. This is the radius, right? This is my radius. Okay, and the height is, let me highlight it with a different color. This is the height of the cone if we're looking at it from a geometric perspective. Okay, that's 3. And look, it's exactly the same number, pi. Okay, all right. Now, if a problem is given to you and it says use any method from calculus 2 to compute the volume of this object, you can go ahead and use the disk method. Okay, or you can use the shell method. But I do want to emphasize that in calculus 2, I am not interested in seeing your solutions for geometry, right? So as you want to check it, that's fine. But we're using integration methods to find volumes of these objects, not just simple geometry. Okay, let me stop right here. What do you guys think? Any questions? Anything that we need to discuss? Someone say something, please. Otherwise, I feel like I'm disconnected or...
Makes sense.
Yeah. All good? Okay. All right. Okay, we got 2 more examples, so we're going to go a little bit quicker because we know what to do now, except we have rotation of R in a different direction. Okay, so here I have example 3 and 4, and we're going to be revolving our R about the x-axis. Okay, so let's see how we handle these situations. Business as usual, as far as the initial step, we got to make a nice picture. Okay, so here's our x and y plane. We have functions. Y is equal to square root of x. Okay, so we know what that looks like. Looks like something like that. Then we have y is equal to 2 minus x. So that's a straight line with a negative slope. Kind of goes something like this. And then we're gonna go this way. Okay, so we have some curvature over here, and this is a straight line. And y is equal to 0. That's the x-axis. So here's our piece that we're going to be revolving about the x-axis. I'm going to highlight important part. About x-axis, that means everything in terms of y. Okay, now I need to set up my integral where the function is y, the variable is y, and the limits are also in terms of y. Okay, let's see. What do we have here? Okay, let's go ahead and find this point right here. So for y, this point will be 1. You can set up these two equations and solve for them. Okay, so you set up y is equal to square root of x is equal to 2 minus x. You find your x and then you plug it into one of those expressions. Okay, this is my function y is square root of x. This function right here is y is equal to 2 minus x. Okay, right now everything is in terms of x. That's not how we need it. That's all right. We can rewrite it in terms of y, but let's see the general setup. We'll figure out the limits as our last step. But now I'm going to do 2 pi y. Okay, that is my circumference. Okay, the circumference or the width of each shell. Something goes here, dy. So the top function in terms of y minus the bottom function. The top function, let me highlight that one in green, would be this one. Okay, your heights are now computed this way. These are your heights. So this is my top function. Okay, in terms of y, what is that? Okay, so let me write this over here. This would be x is equal to 2 minus y, and that's what's going to go in here as my top function. Okay, that is my top minus the bottom. What is the bottom? Let me highlight that one in a different color. So let's say blue. That would be this part right here. Okay, that is my bottom function. Okay, in terms of y, what is that? Okay, this is x is equal to y squared. So that's going to go in here. Okay, and that's the setup. All right.
So why would root x not be the top function?
Okay, let me think how to explain it. Let's go ahead and rotate this. Let's say 90 degrees in the counterclockwise rotation direction, right? Okay, so what is that going to look like then? So if you do this, if you flip it this way, so it's gonna look something like this, right? Here's your x, here's your y. You see that?
Okay, yep, I got it. Thanks.
Because this is the positive direction, right?
Yep.
So you want to look at a positive direction. Which one is bigger? That's your top function.
It's like finding the area, top and bottom, f and g of x.
So this is not the area, right? We're finding the height of our shell.
Yeah, it's still the same.
Okay. Now, guys, listen. If this is confusing, this is okay. This is the hardest method. I don't expect you to just get it right away. Okay, it will take you some practice, some time to really understand the method and how to look at the pictures and decide, okay, we're going in this direction, so this is my top and this is the bottom, okay? But I don't expect just immediate understanding of this method, okay? But let me just separate here for a second. What about all of the steps? Are they okay so far? Yes or no? Yes, okay. Oh, we forgot the limits. The limits are for y, so from 0 to 1. Okay, I took out pi, and now here I get a polynomial function. That's easy to integrate. 2y minus y squared minus y cubed dy. Okay, so this is 2 pi. The antiderivative here would be what? So this is y squared minus 1/3 y cubed minus 1/4 y to the 4th we go from 0 to 1. Okay, that's nice. From 0, everything is gone. So we evaluate this at 1. 1 minus 1/3 minus 1/4 times 2 pi. I'm going to let you figure out the details, but you should get 5 pi over 6. That's going to be your final answer for this problem. Okay, let me circle this as your final answer. Okay, let me stop right here for a minute. Take a look at all the steps. Let me know if you have any questions. All good?
Yes, I think so.
Okay, very good. Last problem for this section. Okay, last problem. Another example where we're rotating our about the x-axis. Okay, so thankfully here it's already set up for us in terms of y as our function, but still let's go ahead and take a let's take a nice picture of this problem. Again, whenever you guys are working on, let's say, paper assignments or even on my math lab problems, feel free to use Desmos. It's very nice for graphing functions that are sort of complicated like this one. So I wouldn't expect you to do this by hand. Okay, so what do we have here? Oh, I'm missing one of the functions. So I'll go ahead and add a function y is equal to 1. Somehow it's not in the notes here. Okay, so we have x is equal to 4 over y plus y cubed. So that one, yeah, we should go ahead and use a graphing utility to sketch, and you're going to get something like this. Okay, then we have x is equal to 1 over root 3. So you're going to get a vertical line here. So this is x is equal to 1 over root 3. And y is equal to 1. That's a horizontal line, right? Y is equal to 1. Okay, let me label my sketch. Okay, we are rotating this piece right here. Not really a triangle, right? We have some curvature on that one side. So we're rotating this about what? About x-axis. Okay, so that's going to go this way, right? Okay. All right, let's see. How do we set this up? Let me highlight important parts. X-axis. That means everything needs to be in terms of y. Okay. In terms of y, volume will be the integral. We'll figure out the limits. Okay. 2 pi y. This is our width, right? This is the width of the shell. Okay, and this is equivalent to the circumference of a circle. Okay, times something goes here, the difference of two functions, dy. So now we need to decide what is the top function, what is the bottom. And let me remind you how our height is computed. These are all the heights of our shells, right? Okay, the ones that I'm highlighting with this green color. Okay, let me see if you guys can figure out what is the top function. What do you guys think? What would be the top function here?
Four over y plus y cubed. Oh,
Very good. That's the one. 4 over y plus y cubed. Excellent. That's going to be our top. What about the bottom? Minus what?
1 over root 3.
Yep. 1 over root 3. Very good. That's it. Okay. So that's your top. This function is the bottom. You can go ahead and use Desmos to find these points now to find our limits, right? Our y is restricted for which values? Okay, the first one is 1. We know that much. And then this one is actually root 3. Okay. So root 3 goes up here. We go from 1 to root 3, checking everything. 2 pi y times the top minus the bottom. Yes, that's the setup. Okay, the setup is done. So let me bring it over here. Volume is equal to 2 pi. I'm going to factor this out. We go from 1 to root 3. And now I'm going to distribute my y. So I'm going to get 4y over y plus y cubed minus y over root 3 dy. Okay, let's see. The second part, y over root 3, that's easy to integrate. The first one, you say, well, that's function that we've never seen before as far as the integration goes. And you're right, but we can reduce it by y. And the reason why we can't do it, because we're on the interval where y is not equal to 0, right? So we go from 1 to square root of 3. We're going to go ahead and reduce this by y. Okay, cancel it out. That's the same way of saying it. So then we get 2 pi integral from 1 to root 3. And what do we get here? 4 over 1 plus y squared. And this one doesn't change. Dy. Okay, and now how do we integrate 4 over 1 plus y squared? Do you guys remember how to integrate that? One over 1 plus stuff squared. What is that?
Oh, is it inverse tangent?
That's arctangent, right? Yes, good. So this would be arctangent or tangent inverse, whichever you prefer. Okay, so what do we get here? This is going to be 2 pi. The function that we get is 4 tangent inverse or arctangent, whichever notation you prefer is fine. Okay, minus, and what do we get here? So this is going to be y squared over 2 root 3. We go from 1 to root 3. Okay, I'm going to let you figure out the details. Now this is just a matter of evaluation. We don't necessarily always get nice numbers. That's okay. So the answer here will be 2 pi times 1/3 pi minus 1 over root 3. Okay, so fill in the details of this evaluation. Okay, but that's the problem. That's the last problem for this particular section. So let me project the whole thing on one screen. Okay. Are there any questions that you would like to discuss related to this problem and then the section in general? Nothing? How are you guys feeling about this method?
Feeling good.
Feeling good? Okay.
I feel good about it. I just need to practice more.
That's correct. Yes. Yeah. Practice will definitely be very, very beneficial. So when you guys work on problems on MyMathLab, I hope you have a pile of papers right next to you and you're doing this by hand, okay, before you type in the answers. Okay, the idea is that we should be able to do these problems without any calculations, any calculators, and you don't need calculators, right? If you see that we set up all of these problems, the integration itself is easy. Okay, and that's one hint for you guys from me. If you set up your integral and it looks like it's impossible to integrate, there might have been a mistake, because the way these problems are reverse engineered, right? So they start with some function that's easy to integrate. Okay, no tricks there. So if you see that it's a function we've never done before as far as integration goes, go back and look at your setup. Okay, and you know what happens a lot? Very often, I see students forgetting that y, or forgetting this x right here in the formula. And sometimes, if you're missing that component, your function is not integrable. We actually don't know how to integrate. So that's definitely something to keep in mind. Okay, remember the fundamental idea. It is circumference times the height. Circumference is 2 pi x or 2 pi y, depending on which way we're rotating our object. Okay, so please don't forget that variable, very important. Okay, so now here I have this summary for you guys. Again, you don't need to write this out. I'm going to upload the notes, and this is just in your textbook. So I took a picture of the pages in the book, so we don't have to reinvent the wheel. But let's just take a look at this very briefly and see what the difference is, right? So whenever we have disk method and shell method, okay, this is your first box right here, and we have the same variable. You see how the disk method will have the same variable if we're rotating it about that axis, right? So the x-axis right here. So let me highlight what I'm talking about. X-axis, dx. Everything is in terms of x for shell method. Okay, I'm sorry, for disk method. But once it's shell method, oh, it's a different axis. Okay, now, so if you're doing it y-axis rotation, then everything is in terms of a different variable. Okay, and this is a very important concept to keep in mind. Okay, same idea, integration with respect to y. If we're doing disk or washer method, and we're doing it with rotating r about the y-axis, then yes, everything is with respect to that same variable. But for the shell method, that's different. For the shell method, if we're doing it about x-axis, then we have everything in terms of y. Okay, so again, you do not need to memorize any of this. You can just have access to your notes when you guys are solving problems, whether it's homework, test, activities, anything, right? So just make sure you know how to apply these formulas. Okay. All right. So volume of objects, general slicing method, right? Then we have disk method, washer method, shell method. Those are the 4 to keep in mind for this chapter. Okay. Okay. Then the last thing for today's lecture, we're going to talk about computing lengths of curves. Okay, and here I'm giving you a formula that's, we're not going to go through the whole derivation. If you would like to see how this formula is derived, you can watch the videos on Pearson. Okay, and they go through a nice explanation of why the formula works the way it does. We don't need to worry about the rigorous part of it. Okay, we just need to be able to apply it. Besides, this formula is really kind of like a supplementary part for the next section, which is finding surface areas. So today we're just going to do a few problems for computing the length of curves, and it is not complicated. They just can be a little bit tedious. Okay, as far as the general strategy, so these are my steps that I recommend that you guys do when computing length of curves. Okay, strategy here is this. First, whenever you have your function, compute f prime. And you don't have to break it down in all of these steps, but because these problems can be so messy, I do recommend that you guys just follow these steps. Especially if you don't compute f prime correctly, then none of it matters, right? We have to be able to compute the derivative correctly. So we compute f prime first. The step number 2, square that. Compute f prime squared. Okay. Then we need to compute and simplify the expression 1 plus f prime, let's say, of x squared. Okay, you will notice that for these problems, the idea is always the same, but it's always algebra that's just a little bit tricky. Okay, now at the last step, you should have an expression that kind of looks like this: square root of some expression here squared. We want to have this cancellation of square root and x. So some stuff goes here, and this is the step that's a little tricky. You will just have to remember all of the algebraic steps and be really, really careful. Now, once that's done, then you integrate. Okay, so these problems fundamentally are not difficult. It's just a little annoying because there's so much algebra going on. Okay, so let's go ahead and do that. We'll do 3 problems. They all say find the arc length of the following curves on the given interval. Okay, so I have this exponential function here on the interval from negative natural log of 2 to natural log of 2. And we can sketch it if you would like to see that we'll get this curve, and we want to know how long that curve is. Okay, so I'm just going to follow my steps. Step number 1, compute y prime. Okay, so that would be 1/2 e to the x, and then what do we have here? E to the negative x. Prime of that would be negative 1/2 e to the negative x. Okay, that is my y prime. Now I'm going to carefully square this. So 1/2 e to the x minus 1/2 e to the negative x squared. Okay, this is square of a difference. So we get 1/4 e to the x minus double of this product, right? So it's 2 times 1/2 e to the x times 1/2 e to the negative x. And then plus, oh, I missed a 2 over here, plus 1/4 e to the negative 2x. Okay. So this is why I separate these problems into steps, because they just can get a little bit messy. All right. Okay, so what do we have here? What is e to the x times e to the negative x? Do you guys know what that is? Does anyone know? So e to the x times e to the negative x, what is that?
E to the negative x squared?
I don't
Is
think
it just
that's
one?
the right. Yes, why is it just one? Tell me. You're right.
Is that because it's like e to the x times 1 over e to the x? Or
Yeah, so you can think about it this way, or whenever we multiply in the same base, we get addition of powers, right? So x minus x, that's 0. So this is 1. Okay, let's see. I see Henry raising their hand. Was that you, Henry? Was that what you're going to say?
Yes, it was.
Yeah, good. Okay, so e to the x times e to the negative x, that's 1. Okay, and then 2 times 1/2 times 1/2. That's just 1/2, right? So what we get is the following: 1/4 e to the 2x minus 1/2 plus 1/4 e to the negative 2x. Okay. Then we need to add 1 to this, right? So next step, 1 plus this expression. Okay, so what do we get? 1 minus 1/2, that's going to be positive 1/2. And you will notice what we're going to get, we're basically getting exactly the same expression as what we've gotten when we multiplied that square through, except over here we get positive 1/2, right? 1 minus 1/2, that's the positive 1/2. So let me highlight these two. Okay, but this is a perfect square. This is 1/2 e to the x plus 1/2 e to the negative x squared. Okay, and you might notice that over here the only difference is that negative and positive, right? Okay, and there's going to be some patterns here for certain functions, not all of them, not all of the functions. Okay, now this is good. Why is that good? Because we want a perfect square to cancel out that square root. Okay, so what is our L? Now we can do the last step. So let me put step number 4. Our L is the integral. We go from negative natural log of 2 to positive natural log of 2. Square root of this expression, negative x squared dx. Okay, you will notice that square and square root cancel out. And now we have a nice, easy function to work with. So that's 1/2 e to the x plus 1/2 e to the negative x dx. Okay, this one is easy to integrate. I can pull out the 1/2. What's the antiderivative? The antiderivative is e to the x minus e to the negative x. We go from negative natural log of 2 to positive natural log of 2. Okay. Once you simplify and combine all like terms, evaluate carefully, you get actually a really nice number, 3/2. Units, this is length, right? So that's just units. Okay, so let's project this whole solution. What are the steps that we've done? First and very important step, computing the derivative correctly. Once that's done, we square it. Add 1, simplify, and now we need to do some tricks here. I remember some formulas, right? So that to make sure that we can convert that into a perfect square. Once that's done, reduce your square and the square root, integrate, final answer is nice. Okay. Let me take a pause over here. Are there any questions? All good? I'm still with you guys, right?
Yeah.
Okay, good. All right. If there are no questions, then I have 2 more problems to work through, and then we are done. Okay, let's see. Next problem. I have a function 3 natural log of x minus x squared over 24. I'm just going to stick with my strategy. Okay, do all of these steps one at a time. First thing first, I'm going to compute y prime. So y prime is then what? Natural log of x prime, that's 1 over x. So 3 over x minus, this one would be x over 12. Okay, that's my y prime. Then y prime squared. Okay, what is this one? This one is 9 over x squared, right? Minus the double of these two. So that would be 2 times 3 over x times x over 12 plus x squared over 12 squared. I'm just going to keep that 12 squared as is for now. Okay. What do we get? We get 9 over x squared, and we have 6 over 12, and then x over x. So we just get minus 1/2, right? Plus x squared over 12 squared. Okay. Let me label my steps. Step 1, step 2 is done. Step 3 is adding 1 to this expression. I'm just following the formula, right? So 1 plus y prime squared would be then 1 plus 9 over x squared minus 1/2 plus x squared over 12 squared. And again, we get 1 minus 1/2. That's positive 1/2. So positive 1/2. Oh, that's nice because it's exactly the same as we've already been dealing with, right? So this is a perfect square. This is another perfect square. Which one is it? That would be 3 over x plus x over 12 squared. Okay, now the last step is to evaluate this expression. I'm looking at my limits. Let's see, what are my limits from 4 to 6? So my length is then the integral. We go from 1 to 6. Did I say 4? Okay, so we go from 1 to 6. Square root of 3x plus x over 12 squared dx. Okay, square root and x and square, they cancel out, and that's the whole point of breaking it down. We want this cancellation, so we need to be very careful with our algebraic steps. We get the integral. We go from 1 to 6. What do we get here? This is 3x plus x over 12 dx. Okay. The antiderivative of this is easy to compute, so this would be 3 natural log of x. I don't need absolute value because we're on the positive values for x, right? From 1 to 6, everything is positive. Plus, what's the antiderivative here? This would be x squared over 24. We evaluate this from 1 to 6. Okay, so I'm gonna bring this down a little bit here. What do we get? This is 3 natural log of 6 plus 6 squared over 24, and then minus 3 natural log of 1 minus 1 squared over 24. Okay, natural log of 1, that's 0. Once we simplify all of this algebra, we should get 3 natural log of 6 plus 35 over 24. Okay, of what? This is length, so this would be units squared. Not squared, just kidding. just regular units, right? Okay. All right, so let's see. Here's your solution to example number 2. What do you guys think of these type of problems?
I have a quick question.
Yeah.
Is it always going to be on like step 3? Is it always going to go back to the difference of squares and then you can like condense it like that, or is that not always going to be the case?
That's not always going to be the case.
Okay.
No. For many problems, it will be. But for some functions, and you will encounter those on your online homework, you will need to do a different trick. You will need to like simplify it differently to
Okay.
convert it into a perfect square. But what always will be truth is that it will be a perfect square. It might just be a different type. So yeah, this is a good question because I think a couple of students of mine in my previous classes mentioned that their teachers just said, oh, well, this is how it's going to work for all of these functions. You can just flip the sign here and there and call it a day. And it does work for some functions, but not all of them. So I don't want you to get this false impression that you can just get it like this, you know, just flip the sign and say, this is it. It's not going to work for all of the functions. Okay.
Okay, that's what I was wondering. Thank you.
Yeah. No. Yes, you're welcome. This is definitely a good question, and I'm glad that you asked that. So I think in some high schools these problems are picked up in the way that it does work out all the time, but it's not going to work out for all of the problems on the online homework for sure. So keep that in mind. Okay, let's do one last problem, and we will be done for today. Okay, let's take a look. All right, we have 1 over 3 x to the power 3 over 2 minus x to 1/2. Okay, and we go from 4 to 6. So again, I'm just going to stick to these steps of carefully computing each expression one at a time. So y prime, what do we get here? So this would be 1 over 3 times 3 over 2 x to the power 1/2, right? Minus, this would be 1/2 x to negative 1/2. And now let me simplify this a little bit. I'm going to get 1/2 x to 1/2 minus 1/2 x to negative 1/2. Now you might be wondering if you could use roots for this one. That's fine. Okay, I prefer powers, so this is what I feel comfortable with. Okay, that's step number 1. Step number 2, y prime squared. Okay, we need to square this expression. 1/2 x to 1/2 minus 1/2 x to negative 1/2 quantity squared. Okay, so this would be 1/4 x, right? X to 1/2 squared, that would be just 1, minus double of their product. Let's see what we get over here. And then plus 1/4 x to negative 1/2 squared. That's also going to be x to the negative first power. Okay, so what happens here in the middle? 1/2 and 2 cancel out, and also x to 1/2 times x to negative 1/2. That's just 1. Okay, so we get an expression that looks like this: 1/4 x minus 1/2 plus 1/4 x to the negative first power. Let's go ahead and add 1 to this expression. This is y prime squared. Okay, 1 plus this, you will notice that we're going to get 1 minus 1/2, so we're going to get exactly the same expression, except we're going to get positive 1/2 in the middle. And that is a perfect square of 1/2 x2 1/2 plus 1/2 x2 negative 1/2. Okay. All right, so what is our last step? We're setting up our integral. The length of this curve, we go from 4 to 16. Okay, I'm going to take that square root. Square root and square cancel out. We're going to get 1/2 x2 1/2 plus 1/2 x2 negative 1/2 dx. Okay. The antiderivative would be, let's see, so we add in 1, 3 over 2, and then divide, multiply by 2 over 3. So we're going to get 1/3 here, plus x2 1/2. Okay, this expression evaluated between from 4 to 6. Nope, not 6, 16. Okay. So here you see that you're going to get some roots. Now the number is actually nice, right? So the limits are picked up because in such a way that you can take roots of these. Square root of 16, we know what that is, and square root of 4. Those are nice numbers, okay? Once you work this out, you should get a nice number. This is going to be 62 over 3. This is units of distance, right? We're measuring distance. And that's going to be your final answer. Okay, so let me project this solution here. Finding length of curves or arc length whenever we have a function and we have some range of values, right? Okay, let me stop here for a minute. Are there any questions for this particular problem? Nothing?
Were we leaving out the 1 or just 1/2 x?
Which step?
3.
So I skipped that part. I skipped the details there. We didn't really leave it out, but 1 minus 1/2, it's 1/2, right? So I just skipped the one step of writing it out. But 1 minus 1/2, that gives us positive 1/2, and that's where this value comes from. Okay? All right, so let's review what we've done today. Okay. We talked about the volume by shells method, just the fundamental difference of what we've been doing as far as the disk and washer method goes, right? And how that's different from this new method, okay, volume by shells. We took a look at 2 examples where we were rotating our about y-axis. So everything had to be in terms of x, okay, when we do about y-axis for shell method. Then we had 2 examples where we had rotation of r about the x-axis, and we had to do everything in terms of y. Each time we had to set up our picture first, right? So that's your very first step to do. Make a nice sketch of your problem. Then here's your summary of the 2 methods. And I mentioned that you don't need to memorize this, just have it ready, available to you in some notes, okay? And then length of curve, okay? We need to know this formula, how to apply it, and your optional strategy here is just break it down into steps, carefully compute each step, simplify it, and then evaluate the integral at the end, okay? All right, I'm going to go ahead and stop this recording now, and then you guys can stay online and ask any questions that you might have.